All right, let's dive in. We're going to play detective today and crack a huge chemical case, one that gets to the very heart of why the elements around us behave the way they do.
So, have you ever wondered about this? Why are some materials, just calm, and others are, well, explosive? It's a puzzle that's had chemists scratching their heads for centuries, and it all comes down to the elements themselves. I mean, just look at this contrast. On one hand, you've got sodium, which goes absolutely crazy and can actually catch fire if it just touches water. Then, on the other, there's gold. It's so chill, you could leave it at the bottom of the ocean for 1,000 years, and it would look exactly the same. They're total opposites. So, where does a detective even start the investigation?
Okay, so like any good detective, you start with what's right in front of you. We're going to look at the obvious evidence first, the physical clues, the stuff we can actually see and touch. So, first up, clue number one, malleability. All that really means is you can hammer it or press it into a super thin sheet without it shattering. And, when you think about it, gold and silver are the absolute champions here. Next, we look for ductility. This is the amazing ability of a metal to be stretched or pulled out into a thin wire. It's why we have things like electrical wiring, right? Incredibly useful.
And to give you an idea of how wild this gets, check this out. Just 1 gram of gold, we're talking less than the weight of a paperclip, can be drawn into a wire 2 kilometers long. That is just insane when you really think about it.
And the clues keep coming. We see their luster, that classic metallic shine. They're usually pretty hard. They're great at conducting heat and electricity, which is a big one. And finally, they're sonorous, which is just a fancy way of saying they make that cool ringing sound when you strike them. It's why bells are made of metal.
So with this whole list of clues, you'd think, okay, case closed. Easy. We should be able to sort everything into neat little boxes. But this is where the plot thickens. The case is about to get a whole lot more complicated. So, based on our first round of investigation, here's our working theory, our rules, if you will. Metals are hard, shiny solids with high melting points, and nonmetals are pretty much the opposite. Seems straightforward enough, right?
Well, then we meet the rule breakers, the suspects who just don't fit the profile. These are the elements that make you want to throw your whole theory out the window.
And believe me, there's a whole lineup of them. You've got mercury, a metal that's liquid at room temperature. What? Gallium and cesium will literally melt from the heat of your hand. Sodium's a metal you can cut with a butter knife. Then on the flip side, you have iodine, a non-metal, but it's shiny. And carbon? As a diamond, it's the hardest thing ever. But as graphite, it conducts electricity. So yeah, just looking at them isn't going to be enough to solve this case. This means our first line of investigation pretty much hit a brick wall. We need a more reliable test. It's time to stop just looking at our suspects and start interrogating them. We're going to see how they behave under a little pressure by checking out their chemical reactions. Okay, so here's our interrogation plan. We're going to run them through 3 big tests. First, how do they react with air when you heat them up? Second, what happens when you put them in water? And third, how do they handle acids? This is where we're going to see their true colors. Just take the water test, for example. Now, this is a fantastic clue. You can see a clear hierarchy showing up. Potassium, it goes absolutely ballistic in even cold water. Magnesium is a bit more chill. It needs hot water to get going. Iron is even pickier. It won't react unless you use steam. And gold? Nope, doesn't react at all. We're definitely starting to see a pattern here. We've gathered all our chemical clues. We've seen how different metals react with air, with water, and with acids, and a clear pattern has definitely emerged. Some are consistently way more vigorous than others. So, now it's time for the big reveal. This leads us to the final crucial question in our investigation. Can we take all this evidence, all these different reactions, and organize them into one single definitive list that solves our mystery once and for all?
And the answer is yes, we can. This is it. It's called the reactivity series, and it is the master key to our entire puzzle. It's basically a league table for metals, arranged perfectly in order from the most reactive at the top, potassium, all the way down to the least reactive at the bottom, gold. And just like that, everything falls into place. This one single list is the code that unlocks our original question. It perfectly explains why sodium and potassium are so explosive and why gold and silver are so calm and stable. Case closed. Or is it? Because, every good detective story answers one last question. What's the motive? We know how the elements are ranked, but we don't really know why. The ultimate why is hidden deep inside the atom itself.
And here is the motive. The secret's all about their electron shells. See, all elements have this fundamental drive to get a completely filled outer shell. Chemists call it a valence shell. Getting to that stable state, kind of like the super unreactive noble gases, is the ultimate goal. That drive is what we call reactivity.
Think about a classic pair, sodium and chlorine. A sodium atom has just one lonely electron in its outer shell, and it is desperate to get rid of it to become stable. Chlorine, on the other hand, has 7 and just needs one more to be complete. So when they meet, sodium gladly gives its electron to chlorine, and that powerful exchange is what makes the reaction so energetic.
So when you boil it all down, this simple drive for a full outer shell is the engine behind pretty much all of chemistry. It's the motive that explains why some elements are explosive and others are inert. And it leaves us with one last tantalizing question. What other great mysteries of the universe can this one simple rule help us unlock?